and thank you very much for having me this evening. And sorry I couldn't make it down. As they said, my name is Lara, and today I'll be talking about my PhD work on sourcing critical metals, tellurium, bismuth, and tungsten as byproducts from Björkdal Gold Mine in Sweden. I'm conducting this work as part of the METFTech project and in conjunction with Mandalay Resources. So as I'm sure everyone knows, the transition to net zero comes with vast mineral and material demands, which we need to meet with a minimal environmental impact. So the World Bank estimates that more than 3 billion tonnes of metals and minerals are needed to reach global net zero carbon. And some of these metals and minerals have been designated by various blocs, countries and organisations as critical. So they have a high strategic and economic importance, and they have a vulnerable or limited supply chain. So the three I'm talking about today, the BGS and the USGS, have designated all three as critical metals, and the EU has designated bismuth and tungsten as critical, and you can see on this plot from the BGS that bismuth, tungsten and tellurium sit in that top right quadrant of high criticality. However, mining has an environmental impact too, and indeed gold mining is one of the worst offenders in this respect, as it contributes quite little to the energy transition. It has a very high carbon footprint and tailings footprint. And as you can see from this plot, it has a much higher relative sort of embodied energy, so sort of measure of relative carbon footprint. And you can see this is a log scale on the vertical axis, so nearly 1,000 times more energy intensive than other common metals. So for reference, gold makes up 0.0001% of the metal we mine by mass, but it's 5% of mining's carbon footprint. And on top of that, around half of all investment into mining goes into gold mining. So in some ways, this is actually quite useful because gold is often byproduct rich. And its financial staying power makes it a perfect candidate to look into byproduct extraction for technology metals. So that is what we're doing at Björkdal Gold Mine, which is in Sweden in the Skellefteå belt. It's a very famous mining district in northern Sweden. So it currently produces gold with some silver as a byproduct and processes roughly 1.3 megatons per annum of feed ore. So this is sort of currently the setup. So material is mined, it's processed on site, and then 4 different concentrates are sent off to refiners and smelters in Europe. And some of these smelters and refiners do actually extract these byproducts, so tellurium and bismuth, I think they extract, along with purifying gold and silver. But the mine itself receives no remuneration for any of these value-adding byproducts. And indeed, sometimes if concentrations of those target metals are too high, then the smelter induces a penalty. So there's really no incentive for the mine to optimize for byproduct recovery. And so as a result, those byproducts are not tracked, they're not traced, it's unknown sort of where they are, how much goes to waste, how much stays in those concentrates. And therefore, they're not really recovered as much as they could be. So step one, what am I doing? Trying to trace those potential byproduct metals through the mine. So how much of them is there in the ore? Where do they end up? How much ends up in waste? Which concentrates do they end up in? And then having characterised those minerals and metals and where they are, the next stage of my PhD is to look at possible extraction. And in the last 2 decades, there's been a really big movement towards Deep Eutectic Solvents, which are novel environmentally benign processing methods, which would be suitable potentially for this kind of work. So what did we do? Went to the mine site. So we traced the material from the beginning. So this is sort of where it gets fed in to the mine, right to the cleaner tables. at the end. So here you can see 2 concentrates actually being produced. So this nice shiny gold sand goes and ends up in a lovely bucket of gold, and another concentrate is produced from this material off the right of this table. So here is a simplified breakdown of the flow sheet for the mine. So starting off with your stockpile of blasted rock, gets milled and crushed, and then a cyclone in the center separates larger, more dense material, which goes off into a gravity separation circuit, from less dense and smaller particles, which go into a flotation circuit. And each of these circuits produce 2 different concentrates, so 4 in total. And in order from highest concentration and lowest volume, the heavy concentrate, that bucket I mentioned, the middling concentrate, the flotation, Nelson concentrate, and indeed some tailings. So all of these were sampled, and what's next? Let's do some analysis. So we took a dual approach to analysis, so using the scanning electron microscope, or the SEM, in conjunction with Zeiss mineralogic software, so automated mineralogy, and then we did some bulk geochemistry from ALS. So the really exciting thing about the SEM, I'm sure many of you know, is it's super powerful technology. So you can take crushed rock, use the SEM to identify minerals, families of minerals, get detailed imagery and chemistry, identify those proportions, sizes, whether they're locked inside other phases or whether they're sort of liberated and accessible to a leaching technique, for instance. And it can do this over tens of thousands of different grains and particles. So this is a backscattered electron image, and minerals with a higher average atomic number will appear brighter. So this means you can do a sort of modal mineralogy search, which picks up everything in quite coarse detail, so that 15 to 35 micron pixel size, and a bright phase search, which just limits the search to things which come up brighter. So you can look at those in more detail and get a more accurate picture of the phases going on. So just to sort of illustrate that, this particle over here is a mixture of different silicates, and it's quite dark. This one here is a scheelite mineral, so calcium tungstate, and then quite small, my apologies, but there's a small bismuth telluride, quite bright phase there. So some of the outputs from this, and what did we learn from it? So those 3 metals seem to deport almost entirely into 2 phases. So 99% of the tungsten was found in scheelite, so this nice Barney the dinosaur looking particle here, and sort of 95% of bismuth and tellurium seem to end up in a bismuth tellurium phase, which is quite often found in association with gold. So this sort of central yellow portion is gold or electrum, and then this green mineral around the outside is that bismuth tellurium phase. And you can see that the slightly lower atomic number scheelite comes up as slightly duller than the brighter higher atomic number gold and bismuth telluride. And on the whole, both of these minerals seem to be fairly well liberated, so accessible to a potential leaching in the future. Some interesting textures came back from this as well. So this is an image of a fine intergrowth of silver and bismuth telluride. So if I just zoom in there a little bit, you can see some sort of brighter sections and some darker sections, and some spectral analysis on this showed that indeed some of the tellurium is ending up as a silver telluride, and some of the so it's not just in that bismuth telluride phase, but those 2 still are together, so they still track in the same way through the plant. So that's our mineralogic analysis. And indeed, the different concentrates do have quite different mineralogies. So this on the left here, we have the bright phase mineralogy, so a normalized bright phase mineralogy of that middling concentrate. And you can see it has a much higher percentage of scheelite than those bismuth tellurides. But then in the flotation concentrate, there is no scheelite and a higher percentage proportionally of those bright phases of bismuth and tellurium phases. So not exactly tracking gold, for instance, and very different mineralogies across those concentrates. So now we had a look at that bulk geochemistry, and a few key things to note here. So bismuth, which is on the right here, and tellurium seem to follow quite similar concentrations and enrichments to gold, and sort of the heavy concentrate has the highest percentage of both of all three of those. But even in tailings, there is still some level of enrichment, so potentially something to do with we could do with reprocessing there. And also just a note that common contaminants in gold mining, such as arsenic, cadmium, antimony, are not too high, which is always good. So we looked at the concentrations, but where is everything going by mass? So we tracked those flows, and these are for these numbers from monthly data. So you can see that about 40% of the gold ends up in that heavy concentrate, so that nice shiny bucket of gold, and then sort of split, and there's a sort of 87% recovery of gold. But the tungsten in scheelite doesn't really seem to map this gold flow, and actually pretty much all of the tungsten seems to end up in the middling concentrate and in tailings, which has been confirmed from SEM analysis as well. There's quite a lot of fine scheelite going to tailings. So lots of opportunity for rejigging that processing to recover that tungsten. And then, as I said before, bismuth and tellurium seem to sort of come together as a package, and the mass flow from the geochemistry matches this quite nicely. So you can see, again, although the heavy concentrate has the highest concentrations, by mass, most of the bismuth and tellurium seems to be going into the middling, flotation, and tailings. So putting all that together, and just considering those 4 target elements, it looks like the middling concentrate has the highest proportion by mass of those target elements, but there is still quite a significant proportion going into tailings, and only about 30% of that tungsten seems to be getting recovered. So even if those refiners and smelters were trying to extract that tungsten as a byproduct, most of it's gone to tailings and it's being missed. So to summarise, now we know where they end up. Hopefully we can think about how to change some of that minerals processing schema, and the potential for deep eutectic solvents to recover these vital metals in an environmentally benign process. And the key thing is that extracting as many metals that we're going to need for the energy transition as possible from one single mine, rather than opening up lots of new mines, will minimise the environmental footprint of all of those. So thank you very much for listening, and let me know if you have any questions.